Hi, this is Chris, and we are taking a look at question 20 here in section 4 of SAT Practice Test 3. So what we have here in this graph, they show the relationship between swimming time and heart rate, and we see what we call a scatter plot, which is all these different data points that you see plotted individually. And then we also see what's called a line of best fit, which is this diagonal line, which creates a linear relationship out of the points that you see on that scatter plot. So basically, it's a line that tries to minimize how far away each data point is and show a reasonable prediction of the trend in the data. So let's take a look at this question. It says Michael swam 2,000 yards on each of 18 days. The scatter plot above shows his swim time for and corresponding heart rate after each swim. The line of best fit for the data is also shown. For the swim that took 34 minutes, Michael's actual heart rate was about how many beats per minute less than the rate predicted by the line of best fit. And that's important to understand. The line of best fit is exactly that. It's a prediction. It is not an exact value. The data points that you see, these individual coordinates, those are the exact values, but the line of best fit is just an approximation. So let's look at his swim that took 34 minutes. So we see that right here, and if we zoom in on that data point, that's going to be this point right here. And what they're asking for is, hey, what's this difference in here? How far off was that point from that line of best fit in terms of the heart rate? So we see that the data point itself is here, and since this is a difference of 10 beats per minute, it's broken up into 5 intervals here. So each one represents 2 beats per minute. That would be a value of 148. And the line of best fit, this point right here that's on the line, is right at 150. So we're looking for that comparison between 150 and 148. And here, if we want to know how many beats per minute less, well, as long as we can find those two data points, then we can tell that that is exactly 2 beats per minute less, which is answer choice B. Let's move over to question 21. Of the following 4 types of savings account plans, which option would yield exponential growth of the money in the account? And whenever they talk about exponential, it basically means that you're going to have something that fits this kind of function where you have a base to a certain exponent. And here, this generic relationship between a base and an exponent is reflective of exponential growth. And for it to be growth, we want to make sure that we have a value greater than 1 for the base. So here, for growth, we're looking in this standard form for an exponential function. We're looking for it to have a value of x that's greater than 1 in order for that to represent growth. So let's see which of our answer choices fits that model. So A, each successive year, 2% of the initial savings is added to the value of the account. So that shows that we're adding something each year. So that's definitely indicative of growth. However, are we adding more and more and more each year? Are we going to see a curved nature to our function, something that grows like this? Or would we have something that's linear, maybe growth that looks like a straight line? Well, let's see. It's 2% of the initial savings. And if it's initial savings, does that amount increase year over year? Well, if we're using that 2% based on the initial, then that means that that's going to be just a constant amount, which means that this would actually represent a linear growth. So we can say no to answer choice A on this because we're looking for something that represents exponential growth. Let's take a look at B. Each successive year, 1.5% of the initial savings and 100. So here again, we have initial savings, just like we did in A, and then we're adding something else though. We're adding 100. Is this an exponential amount, or is this going to be a constant amount? And hopefully we can realize here that even if we're increasing the amount that we're adding, if we're adding that same amount every time, this is going to work very much like answer choice A. This is going to represent a linear growth relationship because we have the same amount being added year over year. So let's take a look at C. Each successive year, 1% of the current value is added. So 1% of the current value. Is that amount going to increase from one year to the next? Well, the current value, if the account is going up, then whatever you're calculating as that 1% is also going to go up each year. This one is going to have a curved nature to the function. This one is going to represent exponential growth because that current value is constantly increasing, which means you're adding more and more and more year over year. Our correct answer on 21 is going to be answer choice C. And just to talk through D, 100 is added to the value of the account. So here, that's going to be a constant value. You're adding 100, 100, 100, 100. It's the same amount every year. That's also going to represent a linear relationship. So when they say exponential growth, that just means that you have to have a function where you've got a base greater than 1 taken to a certain exponent, meaning that the amount added year over year is going to continue to increase from one year to the next. Last on this page, we'll take a look at question 22. The sum of three numbers is 855. One of the numbers x is 50% more than the sum of the other two numbers. What is the value of x? So let's see if we could write out a relationship here. We'll go statement by statement. The sum of three numbers is 855. So that would be like saying x plus y plus z. And if that's 855, then they tell us in our second statement that one of the numbers x is 50% more than the sum of the other two numbers, which means that x here would equal 50% more than, which would be like saying 100 plus 50%, 150%, or 1.5 times y plus z. And so here, to put everything in terms of x, because that's the target value that they're asking for. They want x. So we can do a little substitution here. We can isolate y plus z. Since we have a y plus z in our original equation, and we have a y plus z in our equation for x, we can solve for y plus z and get x over 1.5. And then we can plug that in to our original equation. So this would be x plus x over 1.5 equals 855. And to solve for x, so here we would have to multiply everything in this equation by 1.5. That would give us 1.5x plus x, multiplying the whole thing by 1.5 to get rid of that denominator. So 1.5x plus x equals 855 times 1.5, which would be 1282.5. Combine like terms, 2.5x equals 1282.5. Divide by 2.5. And we are left with x equals 513, which matches answer choice B. So as you can see, this is quite a bit of complicated math. We can also look at this in a different way to eliminate a couple answer choices quickly. And that is going to be that if x is more than the others combined, then we know that out of this 855 amount, x has to be more than half, which means that hopefully we can recognize that x has to be one of these larger values here. So even if we can't do the exact math, I think we can still 50-50 this question relatively quickly by understanding that basic relationship there with the information provided. And again, even if you can't find an exact answer, don't discount the value of being able to eliminate a couple options as to how that's going to impact your score. Because if you can 50-50 a tough question like this, as opposed to guessing randomly, you're doubling your chances of getting it right. And that's going to be a really important factor to